Chapter 4, Diving Science. The underwater world presents a new and totally different environment from the air world in which you live. As you descend below the surface, the increased pressure will have direct and indirect effect on your body. However, most of your time underwater you will not be aware of or feel these effects. If you pick up one scuba cylinder with air in it at 1 bar or 1 atmosphere and another just like it filled with air to its rated pressure, the second is about 2 to 4 kilograms or 4 to 8 pounds heavier than the first. This is because the compressed air is more dense. Air has weight. 1 liter of air weighs 1.25 grams. 1 liter of fresh water weighs 1 kilogram, and 1 liter of salt water weighs 1.025 kilograms. In the imperial measurement system, this is expressed as 0.08 pounds per 1 cubic foot of air, or 62.4 pounds per cubic foot for fresh and 64 pounds per cubic foot for salt water. Air is a mixture of different gases. The gases are colorless, odorless, and tasteless. Air is composed of approximately 20.9% oxygen, 78% nitrogen, and 1.1% of miscellaneous gases. The most important component of air to us is oxygen. We cannot survive without oxygen. Nitrogen is a metabolically inert gas. Dissolved nitrogen is present in your body, and additional nitrogen is absorbed in your body when you are under increased pressure underwater. Some divers use special mixtures of gases, such as nitrox, for diving. These mixtures contain different percentages of oxygen and nitrogen than air. Air can be easily compressed. When pressure is applied to a volume of air, it can be forced to occupy a much smaller area. Water cannot be significantly compressed. The density of water at any depth is the same as the density of water at the surface, though the pressure it's under will be greater because of the weight of the water above it. Water affects our vision, our ability to distinguish colors, our hearing, our ability to retain heat, and our ability to move through it as compared to air. The human eye is designed to focus light rays in air. That is why objects appear blurry when you open your eyes in water. The mask allows you to put an airspace in front of your eyes to see without the blur. As light rays pass from air to water, they slow down and bend. This bending is called refraction, and it changes the way you see objects underwater. Objects appear 1/3 closer and larger than they do in air. Colors also look much different underwater. As light passes through the water absorbs the colors of the spectrum of the sunlight. The first visible color to be absorbed is red, followed by orange, then yellow, then green, then blue, then indigo, and finally violet. At greater depths, the only colors you can see without a dive light are blues and purples. Noises sound different underwater than they do in air. Because of the greater density of water compared to air, sound waves travel about 4 times faster in water than in air. The sound waves move so quickly that it is difficult to determine the source of a sound. Because water is much denser than air, water can absorb a great deal of heat without changing its temperature. Also, heat can be conducted out of your body by direct contact with water at a rate nearly 25 times faster than by air. Water resists your movement. This is called drag. If your equipment is sleek and compact, it will be easier for you to swim than if your gear has dangling hoses and loose straps. The more you can streamline yourself and your equipment, the easier it will be for you to move through the water. Buoyancy is always an upward force tending to cause you to float, rise, hover, or sink less quickly. As a diver, you control your buoyancy primarily by the amount of weight you wear and the amount of air you have in your BC or dry suit. If an object floats, the object is less dense than the water. You want to have enough buoyancy to float when you are at the surface before and after you dive. If an object is neutral, it hovers. You want to be neutrally buoyant throughout your dive. If an object displaces an amount of water that weighs less than the object does, it sinks or it's negative. Your weight and your volume affects your buoyancy. Making a dive in a wetsuit, your buoyancy changes over the course of the dive. As you descend, the pressure of the water increases and compresses the gas bubbles in your wetsuit. As the bubbles compress, the wetsuit displaces less water and therefore loses some of its buoyancy. You will notice that you are sinking faster and faster the deeper you go. To compensate for the loss of buoyancy, you must add air to your BC, which increases your volume to regain the lost buoyancy. As you ascend, the bubbles in your wetsuit and the air in your BC will expand because the pressure of water is reduced. You will notice that you are rising faster and faster. To compensate for the additional buoyancy, you must vent air from your BC to control your ascent. The density of the water in which you dive also affects your buoyancy. Salt water is about 2.5% denser than fresh water because of the weight of the minerals dissolved in it. If you are weighted to be neutral in salt water and you dive in fresh water with the same amount of weight, you'll sink. You must recheck your buoyancy if you change from diving in salt water to fresh water and vice versa. When you descend in water, the force from the weight of the air and water above you affects you. This force is called pressure and is measured in bar or pound per square inch, or psi. If you weighed a column of air that was 1 centimeter by 1 centimeter and extended it all the way to the edge of the atmosphere, you would find it weighed about 1 kilogram. If it were 1 inch by 1 inch, it would weigh about 14.7 pounds. In other words, this column exerts a pressure of about 1 bar, or 14.7 psi. This constant is called 1 atmosphere of pressure. If you took a column of fresh water that was 10.3 meters or 34 feet tall and weighed it, you would see that it exerted a pressure of about 1 bar or 14.7 psi. This equals the pressure exerted by the atmosphere at sea level. Therefore, 10.3 meters or 34 feet of fresh water is equal to 1 atmosphere of pressure. If you took a column of salt water that was 10 meters or 33 feet tall and weighed it, you would also see that it exerted a pressure of about 1 bar or 14.7 psi. This equals the pressure exerted by the atmosphere at sea level. Therefore, 10 meters or 33 feet of seawater is equal to 1 atmosphere of pressure. Pressure in water increases at a constant rate, and it's cumulative. Pressure in salt water also increases at a constant rate, and it's cumulative. 10 meters or 33 feet of salt water is 1 atmosphere. 20 meters or 66 feet of salt water equals 2 atmospheres, and so on. You can refer to pressure in 2 different ways, absolute and gauge. When you dive, the pressure of the water as well as the pressure of the atmosphere push on you. At sea level, you are already under 1 atmosphere of pressure absolute. At a depth of 10 meters or 33 feet, you are under 2 atmospheres of pressure absolute. 1 atmosphere from the air plus 1 from the salt water. At 20 meters or 66 feet, you are under 3 atmospheres absolute, and so on. Because atmospheric pressure is nearly constant at sea level, most diving depth gauges are calibrated to read 0 at sea level. When a depth gauge indicates 10 meters, 33 feet in seawater, it is saying that the pressure is 1 atmosphere greater than it was at the surface. The pressure on such a gauge is called gauge pressure because it ignores the 1 atmosphere from the air above the water. You always use absolute pressure when determining the total pressure being exerted on your body at any depth. For example, you descend from the surface to 10 meters or 33 feet of salt water, you are doubling the pressure on your body. 20 meters or 66 feet, you are tripling it. If you invert a bucket, force it below the surface of the ocean, and take it to depth, the pressure surrounding the bucket increases and compresses the air in the bucket. When a bucket gets to 10 meters or 33 feet of seawater, or 2 ATA or atmospheres, the pressure has doubled on the bucket. The volume of air in the bucket has decreased to half of the original surface volume. When the bucket has descended to 3 ATA, the pressure triples and the volume of air has decreased to 1/3 the original. The inverse relationship between pressure and volume is known as Boyle's law. If you were to maintain the volume of air in the bucket by adding air through a hose during descent, the air would match the original volume. You take the bucket to 10 meters, fill it with air, and raise it to the surface. As the pressure decreases from 2 ATA to 1 ATA, the volume of air doubles. The bucket cannot hold this increased volume, so the excess air bubbles out the rim. If you took the bucket to 30 meters, filled it with air, and raised it to the surface, a volume of air equal to 3 buckets would escape, and the volume equal to 1 bucket would remain. The effects of pressure on a closed system is much more dramatic. If you take a sealed plastic bag filled with air down to depth, the bag becomes smaller and smaller. When you return back up, the air expands and the volume increases back to its original size. Now imagine that you take the same bag down to depth, open it, fill it with air back to its original volume, and close it. When you bring the bag back up, the air expands, but it cannot escape. The bag will expand slightly, but it will finally burst. The only way to prevent the bag from bursting is to vent the excess air during the ascent. The same thing would happen to your lungs if you took a deep breath from a scuba regulator at depth, held it, and then swam toward the surface. You must never hold your breath when breathing compressed air underwater. The greatest change in pressure is between the surface and 10 meters or 33 feet in saltwater. The pressure doubles from 1 to 2 ATA. As pressure increases, air compresses to a smaller volume. As the air compresses, it becomes denser. At 2 ATA, air is twice as dense as it is on the surface. As the air you breathe becomes denser, it does not flow as easily. When you scuba dive, you breathe air that is compressed to the ambient pressure at your depth, which is much denser than the air at the surface. The deeper you dive, the more resistance there is to the flow of compressed air through your regulator hose and through your passages. This puts limits on how hard you can exert yourself underwater. The deeper you dive, the denser the air, and the faster you empty your cylinder. The rate at which you consume air in your cylinder is directly proportional to the depth of your dive. You consume your air twice as fast at 10 meters as you do on the surface, 3 times as fast at 20 meters, and so on. The other factors that affect the rate at which you consume air are your activity level during the dive, your mental state, your body size, the warmth of your diving suit, and your physical fitness. Besides depth, physical activity has the greatest effect on your air consumption underwater. You can use up to 4 times more air when you are exerting yourself than when you are resting. As a diver, you need to think about developing a slow and relaxed breathing pattern. When you swim fast underwater, you breathe more deeply and more often. Therefore, you use more air. Another factor in air consumption is your physical size. Larger people have larger lungs and use more air than smaller people. To compensate, larger divers will sometimes use larger cylinders. Most sport divers do not calculate their air consumption before each dive. They keep a record in their logbooks of how long their air lasts at different depths and conditions. This enables them to make rough predictions. They monitor their submersible pressure gauges, dive timers, and dive computers, and use the information from these instruments to determine when to begin their ascent. When you dive, the pressure of the water affects your air spaces as well as your breathing. The air spaces include your lungs, sinuses, and middle ears. You can also have air spaces in your stomach, intestines, and teeth. There are also 2 air spaces outside your body that you need to consider when diving. Those are your mask and dry suit. Pressure can affect these spaces in dramatic ways, called the direct effects of pressure. When you descend, the pressure on your body increases at a rate of about 0.1 bar per meter, or about 0.5 psi per foot of depth. Whenever the pressure outside an airspace is greater than the pressure inside an airspace, the situation is called a squeeze, and it can cause damage to your body. This is known as barotrauma or pressure injury. The types of squeezes divers experience are in your sinuses, middle ear, or mask. You can avoid each of these squeezes by proper use of equalization techniques. A reverse block is the opposite of a squeeze. It occurs when the pressure inside an airspace is greater than the surrounding pressure. Blocks can occur during ascent. The airspaces inside your middle ears are especially important when you dive. You must be able to equalize the pressure inside your ears to comfortably and safely dive. Your middle ear has an airway, the eustachian tube, that links it to the back of the throat. Your middle ear transmits sound waves from your eardrum to the auditory nerves of your inner ear. Your body's balance mechanism is contained in the inner ear. If you have a sudden change in pressure or temperature in one ear and not the other, you can get dizzy or experience vertigo. A middle ear squeeze occurs when the air or water pressure in your outer ear is greater than the pressure in your middle ear. You equalize your middle ear by moving air from your throat through the eustachian tube into your middle ear. If you cannot equalize your ears during a dive, you must end the dive and return to the surface. As you descend, the pressure on your outer ear increases and pushes in on the eardrum. If the pressure continues to increase and is not equalized, pain will be felt. The eardrum flexes in to help equalize the pressure and can rupture, allowing water to flow into the middle ear to equalize the pressure. Before you feel the slightest pressure in your ears, you need to equalize. Some divers can equalize by swallowing or wiggling their jaw, but most divers require a bit more effort to open the eustachian tube and equalize the pressure. The most common method for equalizing is simple. You close your mouth tightly or block it with your tongue if on scuba, close your nostrils by pinching them shut, and exhale lightly. As you build up pressure in your head, you should hear the pressure open the tube, a gentle pop. You must never force this technique. You could seriously damage your ears. The key to successful ear equalization is to keep the pressure difference between the water and the middle ear to a minimum. This means that you must equalize early and often, starting at just beneath the surface. If the pressure difference between the inside of your ear and the water becomes marked, the pressure will hold the eustachian tube closed. Once this happens, it is unlikely that you can do anything at depth to open the tubes. Your better choice is to ascend a few feet and reduce the pressure difference until the tubes will open, and then attempt to equalize again. In some cases, you will have to return to the surface and start the descent over. Never try to equalize pressure in a squeezed ear by performing forceful blowing. Blowing hard against a closed nose and mouth will not open your eustachian tubes if they are held shut by pressure. Descending feet first also makes equalizing much easier for most people. Always remember to equalize early and often. If you have a head cold, you must not attempt to dive and equalize by any method. Never use earplugs for skin or scuba diving. Earplugs trap air between themselves and the eardrum, and there is no way to equalize this airspace. A reverse block can occur if your eustachian tube becomes blocked while you are at depth. If you begin to ascend and your ear hurts and feels full, stop your ascent and descend until the feeling goes away. Swallow, wiggle your jaw, and start ascending slowly. You might need to repeat this technique throughout your ascent. If the block does not equalize and you must surface, close your nose and mouth and breathe in. If nothing works, ascend as slowly as possible. Your head has 4 sets of sinuses. Each of your sinuses is connected to your nasal airway by an air passage. Under normal conditions, the passages are open. When you have a cold or congestion, the sinuses will clog. If air is trapped inside a clogged sinus and you attempt to dive, you will feel pressure on your sinuses. If you continue to descend, the soft tissue surrounding the sinus will be pushed into the sinus as the tissues react to equalize the pressure. This is quite painful and can cause blood to flow into the sinus and fill it. If you cannot equalize your sinuses normally during descent, it will fill with body fluids. Then, during ascent, the air in the sinus will try to expand to its original volume, but it can't because of the fluid. Pressure builds in the sinuses and pain results. Blood can be forced out of your nose, mouth, or mask. Any gas that forms in your stomach or intestines during your dive will expand during ascent. This can cause discomfort. To prevent this situation, avoid eating gas-producing foods before you dive. If you have an imperfect filling in one of your teeth, air can get under the filling. When you descend, the air in the space can compress, causing pain. Upon ascent, the compressed air can loosen the filling or fracture the tooth. As the water pressure increases during your descent, the mask is pushed against your face and the air inside the mask compresses. If you don't add air to your mask, the air pressure inside the mask will cause your mask to suck tightly on your face, causing tissue damage. This is known as mask squeeze. You should never have this type of injury because you can easily equalize pressure inside your mask by simply exhaling a small amount of air through your nose into the mask. If you wear a dry suit, you have an airspace surrounding your body. As you descend, the air in the dry suit will compress. To keep the suit from squeezing, simply add air to the suit using the power inflator valve. Whenever you breathe compressed air under pressure, you are exposed to the risk of a lung overexpansion injury. These injuries are rare and most divers never experience them, but they are life-threatening and you must understand their causes and how to prevent and deal with them. Under normal conditions, as you ascend, you breathe in and out in a relaxed manner. You exhale the compressed air from your lungs before it can expand as a result of the decreasing pressure. If you hold your breath, you can suffer a serious lung injury. With your airway closed, the air expanding in your lungs will cause the alveoli to rupture soon after they reach full volume. There is no sensation of discomfort that warns you when this rupture is about to occur. This type of accident most commonly occurs when divers panic and make a rapid ascent holding their breath. As long as you breathe normally during ascent, there is little danger of suffering lung overexpansion. The most serious result of lung overexpansion injury is an air embolism or arterial gas embolism. The greatest danger in this situation is that a plug of air will block the flow of oxygen to the brain. An air embolism can cause unconsciousness, paralysis, brain damage, even death. It's one of the most serious of all the diving accidents. If a lung ruptures and the escaping air gets into the pleural lining surrounding the lungs, the escaped air can cause a condition known as pneumothorax, which is a collapsed lung. Tissue emphysema occurs if air from a ruptured lung escapes in the chest cavity below the breastbone. Your breathing rate is not controlled by the amount of oxygen, but by the amount of carbon dioxide in your bloodstream. The more carbon dioxide you have in your blood, the more you want to breathe. Because pressure and density are different underwater than on land, you must modify your breathing to accommodate these differences. Generally, for maximum efficiency, your breathing should be slightly slower than normal and deeper than you usually breathe. One mistake that divers make is to breathe too shallowly, which causes carbon dioxide to rise. You can also get into trouble if you deliberately breathe deeply and rapidly. This type of breathing is called hyperventilation and has the effect of lowering your body's carbon dioxide level. Skip breathing is a dangerous technique some divers use because they think it will extend the amount of time their cylinder of air will last underwater. When a diver skip breathes, he holds each breath for an extended period of time. If you hold your breath, there is the danger of lung overexpansion injuries. In addition, skip breathing builds up carbon dioxide in the body. You should also avoid overexertion underwater. Regulators have a limit as to how much air they can give you. Stop what you are doing, rest, and breathe slowly and deeply until you recover. By taking it easy underwater, you can avoid overexertion. Even a few drops of water can cause you to cough or choke. Keep your regulator in your mouth and choke, cough, or sneeze right through the mouthpiece. Do not ascend when coughing or choking. When you breathe in and out, the air you breathe is 78% nitrogen. The pressure of nitrogen is balanced between the air and your body. This state is called equilibrium. Under increased pressure, the air you breathe is denser and the partial pressure of nitrogen you inhale with each breath is increased. The pressure of nitrogen in the air you're breathing is greater than the pressure of nitrogen in your body. Your body ingasses nitrogen until the partial pressure of nitrogen in the air you breathe is equal to the pressure of nitrogen in your body. When you ascend, the pressure decreases and the partial pressure of nitrogen decreases. Now the pressure of nitrogen in your body is greater than the partial pressure of the air you are breathing. To compensate, your body off-gasses